and my name is Muraki, representing Green Ammonia Consortium, affiliated organization of the Ammonia Energy Association. Appreciate a very strong and positive message of the Dr. Finkel on hydrogen, and particularly the ammonia in the maritime market. Today I will explain the implementation plan of the carbon-free ammonia value chain. Okajiman, please. Okay, and next page. Yeah, we are planning to utilize the green and blue ammonia as a carbon-free fuel for energy market, like a power generation market for mixed combustion in the coal power plant, gas turbines, and the fuel cells, and the industrial market for industrial furnaces, and as Dr. Pavel mentioned, that the maritime market for marine engines, or possibly the solid oxide fuel cell for marine transportation. And in our study on the blue ammonia from natural gas, it is possible to take ammonia at $340 per ton. At Japan, it is equivalent to $2 per kilogram hydrogen, which is the required level of the price to use hydrogen extensively in the power and industrial market. And at the bottom, the IEA indicated in the report of the G20 in 2019 in Japan, taking into the account of all cost components, ammonia is likely the cheapest mechanism for imports to Japan from Australia. That clearly mentioned that ammonia could be the viable option to transport hydrogen across the ocean. Next page, please. We have several potential supply projects from different areas. In North America, Canada, and the US, mainly the blue ammonia from natural gas, and from Middle East, blue and green ammonia. But particularly, Australia has several projects of the green ammonia, or green hydrogen and green ammonia supply. So I would say that Australia is the highest potential supply country for particularly in a green ammonia. The next page, please. This is our implementation plan of a carbon-free ammonia value chain. First stage of the utilization, we are planning to use ammonia in the mixed combustion in the coal power plant. And at the same time, we will develop the ammonia supply infrastructures in Japan. And the supply side, the market entry will be achieved by cost-effective blue ammonia first. And to the second stage, we will expand the utilization of ammonia in the distributed power system, small, medium gas turbine, solid oxide fuel cell, mixed combustion in the combined cycle gas turbines, industrial furnaces, and maritime market. And according to the expansion of market, the blue ammonia will still lead the position. However, that green ammonia will be introduced, and scale up the green ammonia supply can enhance the cost reduction of the green hydrogen production and make the green ammonia to be the viable option. And third stage, final stage, is a carbon-free power generation by single-fuel ammonia combined cycle and large-scale green ammonia supply and continuous supplies of the blue ammonia for global fuel ammonia market. Next page, please. This is our roadmap of ammonia supply in the coal power plant. We are now conducting a feasibility study to convert to the mixed combustion of the ammonia for the 1 gigawatt coal power station, and we are planning to go into the large-scale demonstration and the facility design from 2021 through 2023. During the time, the final investment decision will be made, and the 1 gigawatt coal power station will be modified to the mixed combustion of the coal of ammonia. And it will take about two years to implement. So 2025 or 2026 will be the start of the commercial use of fuel ammonia in the power market. And we will gradually expand the use of ammonia into the gas turbines, the solid oxide fuels, industrial furnaces, and the marine engines through 2030. And when we start the commercial use of ammonia, the total volume will be 500,000 tons to 1 million tons. 1 gigawatt power station with the 20% mixture of the ammonia requires about 500,000 tons per year. So 1 or 2 units will be 500,000 tons to the 1 million tons. And the supply side, as I mentioned, that the blue ammonia will start the market. And then green ammonia will come on stream through the 2030s, and beyond 2030, blue and green ammonia will be supplied to the large ammonia market. The final page is the key actions of the implementation. The bilateral partnership between Australia and Japan is essential to develop the ammonia value chain. The support from the government for the pilot and trial demonstration project, and also the partnership of the government to develop the common standard regulations and the certification, which Dr. Finkel mentioned in his opening remark. And of course, the partnership between the industries are essential. But to start this new project and new value chain, we need to have strong collaboration between the industries and government of the supply country and demand country. And we expect that market will be expanded not only in Japan, but in Asia market. Particularly Asia has a very large number of the coal-fired power plants, which is required to reduce the carbon dioxide emissions in the next 10 to 20 years. So ammonia will take a big role in this regard. Thank you very much.
Thank you, Jacinta, for the introduction. So today, together with Dr. Bryan Suryanto, and on behalf of the entire ammonia team here at Monash University, we would like to provide an update on the recent developments in high-rate, high-selectivity lithium-mediated nitrogen reduction to ammonia. So it is well known by now that nowadays ammonia is primarily used as a fertilizer in the agriculture sector. But with that being said, it is our vision that the use of ammonia could go far beyond that and would become an important sustainable fuel for global use in the future. So what part do we play in all of this? So our team is working on the development of electrolyzer that you can see here on in the center. And of course, its components for electrochemical ammonia production at ambient temperature and pressure. So of course, ideally, this electrolyzer would be supplied with water as a hydrogen source and nitrogen that is separated from air. This goes without saying that it would be powered by energy coming from renewable sources to produce required quantities of non-Haber-Bosch ammonia. So, but of course, is there a challenge? Of course there is, and the biggest challenge is the nitrogen. So nitrogen is highly non-reactive molecule. I would say it's among the happiest molecules to be on its own there is. So fundamentally, triple bond is there for a reason, hence high temperature, high pressure Haber-Bosch process is required to produce required quantity of ammonia. The second big challenge is, of course, especially if we're talking about the aqueous media, is competing hydrogen evolution reaction. So is there any chance, or is there any way that we can suppress hydrogen evolution reaction to achieve high selectivity toward ammonia? So this brings us to this slide. So where quite recently our team has an article in Joule Journal that is called A Roadmap to the Ammonia Economy, where we try to basically summarize potential direct electrochemical ammonia production modalities. So we split them basically in two groups. It's a direct electrocatalytic and mediated process. So as you can see, we pointed out here for the direct electrocatalytic aqueous modality, the question marks. So these question marks simply indicate the uncertainty in the reported results. So there's a strong growing view on the subject of nitrogen reduction reaction carried in aqueous media that the obtained results are rather, unfortunately, false positive, and primarily due to nitrogen containing contaminations. So nevertheless, our team, we decided to choose a mediated approach, mediated continuous approach, which has potentially be used for highly selective and energy efficient and high rate production of ammonia. So of course, we're not the only ones. We're not the only team that's working in that direction. So there are numerous reports have been out there. So you can see them here on the right-hand side of this slide. So starting in 1994. Nevertheless, I need to point out, so all the state-of-the-art technology or process, not technology yet, but the process is operated at constant current mode, and sometimes it drives the cell voltage of up to 20 volts. So here also I have the example of basically the electrochemical cell where we use lithium ion as a mediator. So basically lithium upon the electric current is reducing to lithium metal, which is rapidly reacts with the supplied nitrogen to the cell, forming a compound that is called the lithium nitride. And of course, freshly formed compound lithium nitride reacts with a proton carrier, in this case is ethanol, to release ammonia. So ideally, of course, we would like to recover the proton carrier, so by supplying protons into the system that are coming from the proton source of water. So we basically applied in our research, yes, the similar strategy, but to gain somewhat better control of the process, we used a constant voltage instead. So we tested our system against numerous parameters. So there are a number of technical parameters, so which I'm not going to go through, but among the important ones are temperature, adjustment of temperature, pressure, the type of solvent used, the type of mediator, or lithium salt use, so the proton source applied voltage, and so on. So overall, as you can see on the right hand side, so we achieved average selectivity towards ammonia production of 35%, with occasional spiking up to 40, 50, and 70%. So that says that still system needs to be adjusted. Also, just to push further to explore the effect of those parameters, because there is an obvious lack of reports in the last 3 decades dedicated to the studies of NRR in non-aqueous media, especially with respect to the electrolyte engineering. So with that being said, now I would like to pass this presentation over to Dr. Bryan Suryanto, who will update you on the recent achievements which have been done in our team in that matter. So Bryan, off to you.
Thank you very much, Dr. Cherepanov. This was an excellent presentation. So just to comment on again the issues that Pavel mentioned earlier in this presentation, which is in the past 3 decades, there barely has been any improvement in the electrochemical cell performance. Voltage, required voltage is still very high, about 20 volts. And also the selectivity is also quite low, about less than 50%. So we believe that maybe the fundamental issues is due to the lack of material innovation. And what do I really mean by this is that in the past 30 years, the electrochemical cell component, such as the solvent, the mediator, proton source, has barely changing at all. THF is still the typical solvent of choice, and also ethanol is still the part of the most widely used electrolyte component, and basically there have been any development on the choice of materials for the electrode. So we believe that maybe electrolyte engineering is the key in solving in all of these challenging issues. So what do we mean by that? We need to develop a new class of electrolyte that has a high ionic conductivity to support high production rate of ammonia, a low water solubility to suppress the side reaction that might hamper the selectivity of the cell, and also ultimately the electrolyte has to be chemically stable and non-sacrificial for it to be able to be implemented at commercial scale and to be technologically relevant. So this is precisely what we have been doing in the past 5 months. And we have developed a new formulation or new recipe of electrolyte. And unfortunately, although we are very excited to share with you this formulation, well, we can't right now because this is currently under ongoing patent applications. But for simplicity, let's just call it MU 2020. So basically what we have done is we initially did a very simple test, which is a conductivity measurements. We realized that the electrolyte that we just developed has a conductivity about 30 times higher than that of the conventional electrolyte. The impact of this higher conductivity can be readily seen by the beautiful correlation of the nitrogen reduction performance in terms of ammonia production rate and ammonia selectivity to the nitrogen pressure. The higher the nitrogen pressure that we introduce, the higher the performance that we observe. And we're also quite surprised that the optimum potential that is required to drive the reaction at an optimum rate is only minus 0.75 volt versus lithium redox couples. So that's actually corresponds to a cell voltage that is less than 5 volt. And under this optimum condition, we already been getting a very high selectivity of up to 85% for ammonia. Also a respectable ammonia production rate in the range of 50 gram per meter square per hour. In terms of the stability, we also compared the stability of our newly formulated electrolyte to the traditional system. As shown in the graph, the traditional system operating at just 8 milliamps per centimeter square of current density could only survive for 18 minutes. And it's already exhibiting a very large cell voltage of about more than 12 volt. Whereas our system were able to operate at 3 times the current density, about 22.5 milliamp per centimeter square, and only requires a cell voltage that is less than 5 volts. And it operates more than 20 hours while maintaining a very high selectivity of almost 100%. So where do we see ourselves in terms of a comparison to the literature targets? So there are mainly 2 literature targets that has been frequently used as a reference. The first one is established by Suryanto from CSIRO, and I believe he is part of this awesome audience. So the first target is about achieving 60 gram per meter square per hour of ammonia production rate. A higher target was set by the Department of Energy through the refuel program back in 2016. And the target was about 600 gram per meter square per hour. It is worth noting, however, in the past 3 decades, the maximum literature yield rate has barely achieved the 60 gram target. But in the past 5 months, we have been making multiple breakthroughs, and our maximum production rate actually is around 120 gram per meter square per hour. This actually really put us in a very strong position to finish this ARENA project, meeting the target that has been set by the DOE in terms of production rate. So how are we going to achieve this DOE target? So we, through a strong collaboration that we already have with the University of Wollongong, first we will use the scale-up approach, such as the use of high specific surface area electrodes, such as metal foam, and maybe we can also do analyze the creating an optimum structure of 3D printed metal electrodes for the ammonia production. And hopefully at the end of this project, we will be able to prototype a 1 kilowatt flow cell for a real demonstration of ammonia production from renewable electricity. So with that, I would like to finish this presentation. And of course, all of these achievements wouldn't be possible without the strong contribution and teamwork that we have in the team. Also from the research, from our research funders, Australian Research Council and ARENA. Thank you.
Okay, so thank you all for your talks. So I will call on DJJ2, who has the first question. Can you unmute yourself and tell us your name and affiliation and then ask your question, please?
Sure. It's Darren Jarvis here from Incitec Pivot. Thanks to all the speakers for great presentations today. So my first question was, I'm actually just looking back.
It's when will Japanese companies sign up?
Yeah, so basically the question I have perhaps for Muraki-san is just an understanding of the appetite for Japanese renewable or clean ammonia customers to sign long-term offtake agreements at premiums to market ammonia prices. As participants in the ammonia market, often it's the knowledge that that premium is going to sustain is what is required to underpin investment.
Okay, may I answer now? Or
yes, please.
Okay. Regarding the fuel ammonia value chain, we are thinking that to have long-term supply conditions between the supplier and off-taker. And of course, we need to look at the premium value of the carbon-free fuel, but need to be supported by the regulations and the government support to implement the relatively high cost of the carbon-free ammonia at the beginning. In the course of the expansion of the market and supply source, I think the cost will be reduced and becomes more viable and cost-effective option. So in the introduction phase, we need to make certain mechanisms. However, particularly the green ammonia, the advantage of the green ammonia is a stable cost mechanism for long term. It's not fluctuated by the oil price and other prices. So that it can be very well accommodated for supply and demand contract, offtake contract, and that is necessary and essential to create the value chain of the green ammonia. But at the beginning, to start the market, open the market, we will use blue ammonia, which is more cost effective at this moment to go into the market. Am I answering your question?
Sorry, I just remuted myself. Yeah, thank you. I guess it was a question of, are there any examples of market agreements now being made that are based on a grey ammonia plus margin? And is that what you see as the go forward contracting model to support investment in whatever form of cleaning of ammonia, whether it's blue ammonia, green ammonia, or otherwise?
Yeah. We don't have any contract and or agreement between the supplier and off-taker and or market and off-taker, but through the 2025-6 during the large experimental test and start the commercial use, probably we cannot take real carbon-free ammonia either from blue and green. So that case, we will take ammonia from the existing market, which is not the carbon free. It's, we can say, great, but we need to start. We need to open the market. Then, during that time, we will negotiate with the ammonia supplier on the blue ammonia or green ammonia, and what the cost and what the long-term basis cost structure, and then that will go into the real supply of the blue and green ammonia. So it's a step-by-step approach. But the advantage of ammonia is ammonia is already in the market.
Thank you.
Jacinta, you're muted.
Yes, I am. So the next question is from Penelope about blue ammonia. And do you have any particular GHG emissions intensity capture threshold in mind? For example, 40, 60 or 80% CO2 capture rate. That's from Muraki as well. Is that clear? Yeah.
Okay. And we started the discussion on the certifications of the blue and green ammonia that can be accommodated into the existing regulations in Japan, and also probably how it can be accommodated into the system in Australia. So we started discussions within the green ammonia. What will be the reasonable and practical certifications for the blue and green ammonia? We already started discussions with our partners in Australia. And we need to have the private industry, the discussions, and then we need to have the government-to-government discussions to create again a reasonable and practical the certification for the blue and green hydrogen ammonia. So it's in a process. We don't have an answer now.
Thank you, Muraki-san. And Penelope, maybe the last question directed at Muraki-san from Brett Cooper. Brett says, do you see a market in Japan for green hydrogen cracked from imported green ammonia for use in fuel cell vehicles?
Okay. If the ammonia value chain is created and the ammonia price is reasonable price to have a hint of the ammonia to produce the reasonable price hydrogen, I think the hydrogen from ammonia to the fuel cell vehicles. That is the option. We are not planning to use the ammonia directly into the vehicles.
Thank you, Muraki-san. So the next question is from Rob Brown. I think it's, sorry. The next question, we might skip your question, Darren, just because you've already had a turn, from Kenneth Baldwin. I think it's more of a comment. Do you want to unmute yourself, Kenneth, and just repeat that? And tell us where you're from. Okay, so it says, Kenneth Baldwin, I guess he's from ANU. That is why the ANU Energy Change Institute, we are researching certification schemes that allow differentiation based on embedded carbon content that will allow policy instruments, e.g. a carbon price, to differentiate these products anywhere along the supply chain. And there's some links there. David, do you want to comment on that at all?
Oh, no, only to say that the certification of the emissions footprint of the hydrogen is obviously going to be important as we are going to expect a value attributed to the hydrogen that's derived from renewable energy. And I know the CSIRO and others, the Hydrogen Energy Council, and a number of groups are looking to coordinate such a scheme, and obviously internationally we need consistency there, and there are international groups addressing the same issue. So that will be important to recognise the value in renewable-based energy carriers in general, not just ammonia.
Thank you, David. The next question is from Priya. I'm not going to try to pronounce your surname, sorry. Would you like to unmute yourself and tell us where you're from and repeat your question, please?
Hello, thank you everyone. I just had a quick question, and this is more thinking from a larger perspective of how this green ammonia or green hydrogen evolution takes place. So just to give a little background, I work with Air Liquide, and I'm based in Houston in the US. So one of the things is, as I see a lot of these projects being announced, or the work that's being done, all the emphasis is on, of course, the production of hydrogen to make ammonia, but there's also a significant amount of oxygen that's being produced. So is there any understanding of how that would eventually be valorized? Because there is value that's to be had with oxygen. So is there anything that we are seeing in the current markets that these green hydrogen and green ammonia markets are targeting, that oxygen could be used as well? And that could possibly be something that could potentially help in the cost scenario as well.
So who do you see that question for, Jacinta?
I think it's yours, David.
Okay. Look, I think there are a number, and the electrolysis people will talk some more about that, I guess, but there's a number of pathways where electrolysis and other paths to hydrogen could be quite symbiotic. You imagine a gasification process and an electrolysis process side by side, potentially utilising that oxygen, or synthesis with other, integration with other production of other carriers. So there are people looking at that, and obviously we wouldn't want to be, at the end of the day, you're putting in a lot of energy to separate oxygen and hydrogen, and we have industrial needs for oxygen, and I'm sure they will continue. So obviously that will have to be considered, and it's an investment in producing hydrogen and oxygen from renewable energy, and you would need to be integrating that with other, displacing, if you like, other oxygen processes wherever possible. And that'll depend on the location, it'll depend on opportunities to get synergistic activities happening together, very similar to some of the utilisation end of the process too, where we want to get synergies between, for example, cracking of the hydrogen and use of hydrogen from ammonia, and potentially power generation from ammonia at the same site. You could use the heat from that to support the cracking. Likewise, I would see the oxygen being synergistically used in systems, but some of the industrial partners in the industry may have a more direct answer to that.
Thank you, David. The next question is for David as well. It's from VXP6. Would you like to unmute yourself and tell us who you are and where you're from?
Yeah, my name is Venkat Pachabatula. I'm from Incitec Pivot in Brisbane.
Yeah, we can hear you. Thanks.
Sorry?
Yep. Do you want me to read your question?
Yes, please. I can't see. Yeah.
Fair enough. Does CSIRO plan to have a pilot plant for low pressure ammonia synthesis loop?
The answer will be yes one day if the early work is successful, as we hope. At the moment, this is early stage research, and it's, as I said in the presentation, there are some here and now technologies which we must start, and there are some which will fit into this roadmap as we move forward. So this is early stages. Pilot plant means different things to different people. We're still at the bench scale. I'm happy to pass to my colleague Shigeru, who might give some indication of what scale would be practical for a pilot scale of this. But at this stage, our projects that we have at the moment are in partnership with ARENA and with Orica and GRDC, as I said, and there's and that's the scale we're at, early stage, low TRL. But it's clearly our plan to move these up that TRL chart. So I don't know if you have a comment you'd like to add there.
Okay, Shigeru here. Regarding this technology, we are about, I think, TRL 5 or so, and we have achieved ammonia production rates, quite similar to what we can achieve in Haber-Bosch process. But I think probably we are looking at about, I think, kilogram scale. That's what in a year or so. But I think it may take another couple of years, to go to pilot scale.
So, sorry, you are getting a similar conversion like Haber-Bosch, but at lower pressures.
At much lower pressures, about 30 bar or so. So basically, we can use directly hydrogen from electrolyzer, which can itself produce hydrogen at that pressure.
But obviously, there will be issues to address around scaling and costs and all that stuff that we've still got to work through.
Okay. So I'd like to have a discussion later on with you guys if I can get your contacts.
Mm-hmm.
Yeah.
So Jacinta.
It would be happy to follow up.
You guys are welcome to mix at the virtual mixer later.
Thanks, Jacinta.
Thanks, Venkat. So the next question is from Mark Hindman. It's quite a long one, so I'll repost it again. It's for David. Still, we'll go with David until 2:15. Mark, would you like to unmute yourself and tell us who you are?
Okay, my name is Mark Hyman. I'm from Perth in Western Australia. I'm an independent consultant. I have a history of delivering mega projects in oil and gas, and I've got a good understanding of the economics here in WA, be it Wheatstone, Gorgon, Impex, the Northwest Shelf, Pluto, and a lot of the upcoming projects too. Now, when you look at the actual capex and the sustainable capex, the opex that these projects are going to be spending over the next 20 years, then the actual price to sell that LNG is around about anything up to $20 per thermal unit, which is way above the $8 per thermal unit per the Japanese crude cocktail price, which is based on the oil S-curve relationship. And my question relates to, are we using these inputs for the economics? Because fossil fuels here in Australia, in this region, to actually develop and deliver those to market, they're very expensive. And that's a fact, because we have got, over the past 20 years, we have all the actual costs already. And the question is, are we using this to actually commercialize ammonia and hydrogen? Because it's quite evident to me that, well, it's the value is there, it is commercial. We can go ahead and deliver hydrogen and ammonia. So my question is, are we using the right figures in the economics? And that question, I guess, kind of goes hand in hand to both Muraki and David. And it's also a good segue question to the question that was raised by DJJ2, which is what is going to be the green ammonia offtake price to actually get this to happen? Because it can happen if we go ahead and collaborate and we actually deliver ammonia and hydrogen to the economies of scale.
We'll start with David.
Yeah, I'm probably not the right person to answer that from the economics and the and the sort of costs that you talked about. That would probably be better from the industry sector. But clearly, it's going to rely on a value and recognition of a value of having that low emissions footprint. Australia, it does have high fossil fuel prices, so in some areas perhaps that makes it a little easier. But we obviously need a value there to be able to support the shift to renewable energy and to develop the new technologies. I don't know what the right number is. There are clearly targets, and Muraki-san had some very challenging targets of the cost of hydrogen, and the federal government setting what $2 a kilogram or something. And that's a challenge. And like any of these renewable energy projects, particularly in some of the different industry sectors, the value has to be recognised, the decarbonisation pathway. Yeah, I'm not going to guess at what the price is, but somebody in the audience is probably far better positioned than I.
Okay.
Muraki-san?
Yeah, it's not simple. The economics of the hydrogen and ammonia versus the fossil fuels. For instance, if you look back the history of the LNG in 1969, the first LNG came to Japan. LNG price was 4 times of the oil price. Why did Japan started to import LNG is the value of the clean energy because of the environmental issue. And so if we compare the hydrogen or ammonia against the oil, it's much higher. But we need to compare how to decarbonize in the energy market. The cost of the renewables and cost of the hydrogen and cost of the ammonia, we need to compare those different options. What is the most economical way to reduce the carbon dioxide emissions extending for the next 2 decades? So that case, particularly in Japan, the ammonia, blue or green ammonia, can be competitive against the renewable energies in Japan. And other ways, the example is the coal-fired power plant. If we need to reduce the carbon dioxide emissions, the country who has a large number of coal-fired power plants can stop and change to the natural gas to reduce the carbon dioxide emissions by half. However, it costs a lot. So we can compare ammonia to the mixed combustion of coal-fired power plant versus the new LNG or natural gas installation. So that kind of different comparison that we need to make to introduce the free new fuel to the market. This is what we are trying to do.
Thank you, Muraki-san. Okay, we're going to move on to questions for Pavel and Bryan. Where's Uto? You had a question about carbon nanotubes as possible electrocatalysts.
Yes. Hi, everyone. We're Suit over here from Western Milk Products, New Zealand. I was just wondering if that possibility has been tried. I've just heard that the potential for the electrocatalysis with a carbon nanotube is really high. There might be an opportunity of using that. Perhaps you might have used that. I was just wondering whether the results were affected.
Pavel?
Yeah. Yeah. Can you hear me? Yeah.
Yep.
Okay. Thank you, Peter, for your question. As you could see from our presentation, so we were mostly exploring the mediated continuous route. So far we haven't used the carbon nanotubes as a potential electrocatalyst.
All right.
So maybe there is a potential, but also on this point, probably we're still looking for the system to be as simple as possible. So and to eliminate any variables as much as we can. So which probably carbon nanotubes introduce into our system.
Thank you, Pavel. So there's 2 more questions for you guys from Venkat again. Any pilot plants with electrochemical ammonia synthesis reaction by Monash?
Yeah, this is. I think it's kind of intercrossing this question, in-crossing with the question for David Harris, right? Mm-hmm. So we are still, I guess, in let's say I probably would call the advanced early stage of the research, where we haven't gone through any trials on synthesis of the pilot plant. Yeah.
Any bench scale process you have? Laboratory scale?
Oh yeah, so basically at the moment we are still on a TRL5, and I think yeah, by the end of this project we are hopefully to demonstrate this prototype device, 1 kilowatt prototype device. I think that would be around middle of 2021.
Okay, thank you very much.
So I think that also answers Darren's question, how far is electrochemical nitrogen reduction from a commercializable product, TRL7? Does anyone want to add anything else to that?
I think, yes, so as we already mentioned, so we are about TRL5. Mm-hmm. So.
Yep. And this question is from Howard Smith. Would you like to unmute yourself? I can see you, but I can't hear you.
Sorry, Jacinta, that's a rookie error, isn't it?
No.
Thanks very much today. It's been fascinating so far. Look, a very quickie. Sorry, Howard Smith from the Keppel Group. It's a large Singapore conglomerate. Here in Australia, we operate a couple of large-scale chloro electrolyzers, and we also trade ammonia amongst various other things. Look, we're keen to push forward at the utility scale to provide ammonia into the domestic marketplace in the first instance. But fascinated with Pavel and Bryan's research about that single-step process for the production of ammonia. I know you're only at the small scale, guys, but have you been able to get some sort of sense of whether you're going to be more efficient in terms of electricity consumption to generate an equivalent amount of ammonia from your process? And the other big input at scale is water as well too, through the electrolytic process. So I'm just sort of curious, now I get the scaling issues you need to work your way through as well too, but do you think you're going to be, once you've resolved and find its way through, is your hypothesis that you'll produce it on half the electricity as an input, or half of the water, or about roughly the same? Or is it just way too early at the stage?
That's a really good question. But at the moment, basically based on the stoichiometry of the reaction, we are using about 1.5 tons of 1.5 tons of water to produce 1 ton of ammonia. But in terms of energy point of view, I think the cell that we have been recently developing is currently operating at around 85 megajoule per kilogram of ammonia. So that's only 23% energy efficient. But again, the problem with the current system is that we are actually capped in terms of energy efficiency with this technology at around 40%. So we actually actively doing more research in terms of further pushing the barrier of this energy efficiency. And yeah, that's basically part of the research that is ongoing in the group as well at the moment.
Got you.
Yeah. On that subject also, as I just wanted to support Bryan on this one. So we do have a PhD students that are actually actively at the moment researching through the improving energy efficiency of this entire system.
Got you. Just a quick follow-up, if I can, to the guys. So your next one is a 1 kilowatt you're aiming for. What's the how many steps and what's the broad timetable to say get you to utility scale, say to 10 megawatts? Do you, from 1 kilowatt, do you go to 10 kilowatts, then up to a megawatt, then to 10? And is that like a 5-year process? You guys, what do you broadly got in mind? So if I go buy something and set something up tomorrow, I'm just sort of trying to understand how far away do we think before you've been able to prove this thing up to industrial scale? Is it better part of a decade, do you think, or 5 years? What if all things going well for you?
Probably, I would like to maybe just quickly start answering this question is like just to avoid any speculations, maybe because we're still in the lab researches.
Sure.
Probably maybe Professor McFarlane would have a few comments on this one with his vision.
We'll get him to turn off and you can give us your view of the world, Pavel.
Yeah, you want to dial a friend on that one, do you? All right. Yeah, actually, Howard, we do have a plan in that regard, and one that's in the sort of realms of between 100 kilowatts and a megawatt would be a sort of shipping container type size is the sort of thing that that would be, and that's we've got at least a concept design around that already done, and that is, I think, something of the order of 4 years away.
Gotcha. Okay.